My name is Runar, and I want to talk to you about Unison. So, who am I? A little bit about me. I'm a co-founder of a company called Unison Computing, and we're building the Unison programming language in Boston. I'm originally from Iceland, just across the pond from here. And I'm also an author of this book called Functional Programming in Scala, which in America is affectionately known as the Red Book. Okay, so what is Unison? Unison is a new programming language. It has some superficial similarities to Haskell. It's a modern, statically typed, purely functional language. We are developing it in the open. It's an open source project with a permissive MIT license. The Unison runtime currently is written in Scala, and it runs on the JVM. So Unison programs run on the JVM. And it has some unique features and constraints that I want to talk to you about today. So a huge disclaimer, this is very work in progress. There's no developer tooling. Basically, we're building that right now. Basically, libraries are non-existent. And everything that I say here is subject to change. So this is all big disclaimer. All right, so here's the plan. I want to give you the motivation for Unison, like why we're building this language. I want to show you some Unison code. I want to tell you about Unison's somewhat unique approach to names, which is kind of its defining feature. I'm going to rant about error messages. I'm going to hate on Monads. And then I'm going to tell you where we're going with this in the near term. But the overall goal is to plant the seeds of revolution in your minds. I want you to be thinking that programming could be so much better than it is. All right, so this desire for revolution, I want to plant in your minds right now. Okay, so why are we building a new language? To answer that question, I want to take you to the beginning. So when I was a kid, I was 7 years old, I had one of these, a Sinclair Spectrum. Did anyone else have one of these? Yeah, right? Okay, so I loved this thing. And programming on this machine, this is where I learned to program for the first time. And it was hugely fun. I could see and hear my software creations come to life on my television, and it captivated my young imagination. It seemed like anything was possible, and it seemed like anyone could do it. Like even a 7-year-old kid could make awesome things happen on this thing. And so I knew at the age of 7 that I wanted to be a programmer when I grew up. And even now, just looking at this object just fills my heart with joy. But then, I got my first programming job like some years later, and I learned that programming professionally was nothing like this. It was just lots of long hours staring at poorly organized code, thinking, who the heck wrote this? And usually I found out that it was in fact I who wrote that code. And the overall experience was often one of frustration and stress and sort of overwhelming complexity of the sort of overbearing structure of the enterprise. And then I came to functional programming, and programming became sort of fun again. I kind of rediscovered this sort of joy of programming. So I found that building software from compositional pieces that snap neatly together made programming fun for me again. And again, I get this sort of sense of joy when I'm writing software. At least when I'm writing something small and isolated, something that I can readily understand, and something that has a cohesive logic on it and runs on a single machine. Because, these days, if you're writing any kind of large-scale application, you need to make lots of programs talk to each other. So a software system these days is typically not monolithic. It has lots of programs that all need to run on different machines and talk to each other. Right, so obviously you code out some JSON serialization logic or something to make those things talk to each other, or like some protobufs or something. But that doesn't scale at all, and then soon you have lots of little servers that need to interface with different versions of each other, and you have to hire an army of programmers to write all the JSON and protobuf or whatever to get them all to talk to each other. And it's just a huge mess. So the fact is that there's this sort of gap between the things that we can specify using the programming language and the things that we actually need to specify to build large systems. Right, so, and we've been filling that gap with these various sort of special purpose technologies. And this is sort of just like a lot of duct tape and baling wire to make a modern software system work. Now, don't get me wrong, these things are useful. People are doing, you know, awesome work with these things, like they're building robust systems. But these things exist to deal with the things that, you know, we need in order to make a real large-scale system, because our languages basically don't do that. Languages really haven't caught up with the internet age, with the fact that we need to make lots of systems talk to each other. So we're still using languages that largely only talk about what a single OS process is doing. So enter Unison. So with Unison, we want to revisit the assumption of what a program even is. Right, so a Unison program describes an entire distributed system, rather than just what one OS process is doing, and then you have to build all kinds of scaffolding. So the Unison program includes deployment, orchestration, scaling up and down, failover. It could be running like on an elastic distributed computation that deploys itself dynamically to like an AWS autoscaling group or something. So the idea is that you write a single program for your whole system, and then you deploy that system by running the program. All right, so whereas today you might write lots of little microservices that maybe, you know, come up with protobufs or JSON for them to talk to each other, and then like you write a bunch of YAML files to describe the deployment and the orchestration, and like you have managed versions builds, and you have configurations and configuration management. You hire a build czar, and then you fire the build czar. But no, write one program for your whole system, and then you deploy the system by running that program. So you can kind of, you know, think of this sort of marketing here for it. The Unison is the internet as a global supercomputer that you can program simply and directly. All right, so let's see some Unison code. So here is a distributed batch mode MapReduce in Unison. So this does something similar to Hadoop, if you're familiar with that. So this function, MapReduce, will take a function f. It'll take some data set here called list, which is a list of values. The function to perform on each element of the list is called f. So we map that over the list. And then there's a monoid with which to reduce. So a monoid is just a method of combining values together. Okay, so this will potentially spawn computations on a bunch of nodes, accumulate in the monoid in a distributed fashion, and then return a single result. All right, and it's a pretty small Unison program that does all of these things. So here's the type for it. You'll note that the argument f here, so the syntax is pretty similar to Haskell, if you're familiar with that. If you're not familiar with it, it's not really important that you understand what's going on here. The main thing is that this is small and straightforward. There's not a lot on here, even though it's doing a big distributed computation. So yeah, the argument f has access to this sort of remoting ability. So it's a function from a, which is the type of the elements of the list, to some value b, which is the things that we want to accumulate, which has access to this remote thing. And so this remote in curly braces is part of our sort of effect system. So that f could be potentially spawning nodes or deploying code to different servers. So it's able to execute some strategy for distributing and coordinating the computation. Right, so, and of course, you can write your own such strategies. Anyway, I'll talk a little bit more later about the stuff in curly brackets, the effect system, or we're calling them abilities that we track in the types. All right, so yeah, so the distributed MapReduce is pretty small. So the magic that makes this work is that Unison can actually transfer an arbitrary computation to a remote node or to a remote location. For example, the remoting API has a primitive called @, or the current remoting API does. So we just give that some location. Here I'm calling it US East Production. And then we give it a whole quoted program. So the little, note the little tick in front of the parentheses. That means I'm going to quote this program and not execute it right now. I'm going to capture it, and I'm going to send it to US East production and run it there. Okay? So here, like click count could be spawning nodes, pulling them from auto-scaling groups or whatever, and it'll have access to the full remoting API. So when Unison runs this code, it's going to send a syntax tree over the network. It's going to send a Unison expression over the network as a message to the other location. But here's the thing. Will that remote location know what we mean by MapReduce, click count, etc.? Right? So this is where you'd run into trouble when trying to send code as a message payload in other languages. So once the code reaches the other side, you know, like if we say parse that code, then those names might have totally different meanings at that location, or they might have no meaning at all, right? But this works in Unison because Unison doesn't really have names. It doesn't really deal in names. So the human readable names that you see here are just used to communicate with you. They're just used to communicate with a human programmer. The machine does not care about these names. So what Unison actually sees is Unison names, which are deterministic cryptographic hashes of the implementations of the reference. So it communicates those between the nodes. And the hashes are actually 512-bit SHA-3s, not just a few characters long. So they're somewhat truncated here. But anyway, Unison identifies a function or type by a hash of its definition. Okay, so it's uniquely identified. You can think of it as kind of like a pointer into a global memory space that basically holds all definitions and functions and values for all time. So yeah, it's a cryptographic hash of the syntax tree after all the names have been removed. And so then the names are just metadata. So this lets us unambiguously send typed code as data between nodes across time and space. So it's been said that there are two hard problems in computer science. There's cache invalidation, naming things, and off-by-one errors. And like, we're not going to solve all these problems, but in Unison, this naming of things is a lot more flexible, and it matters a lot less. So if we do nothing else, then maybe we've contributed a little bit to the state of the art. Like, I don't know if you've ever been in a heated bike shedding session about like what to name something. Don't you like the color of this bike shed, by the way? It's pretty awesome. So in Unison, you may never have to bike shed about names again. Like, if you don't like the name of something, you can locally rename it. And that's a trivial, non-breaking change. No one has to be able to see that you've changed the name. But if you want them to be able to see it, you can publish your naming schemes for others to consume if they wish. For example, these two functions here have the exact same implementation, but they have two different names. So currying takes a function that takes a pair, and it turns it into a function that's curried that takes the arguments one at a time, so you can partially apply it. And sometimes this is called Schoenfinkeling, and so you might want to use a different name for this thing. But in Unison, these are not two different functions with the same implementation. They are the same function. It just has two different names. So they have the same hash, and if you have both of these definitions in your code base, Unison will just attach metadata to that hash with both of those names. Okay, so that it implies something. It implies that the Unison code base is not a mutable bag of text files on your disk. It is an immutable structured object. It's like a purely functional database. And just to kind of show you that here real quick, just captured my screen. So I'm on my master branch on my Unison node, and I say like, okay, show me all the things in the code base called drop. And it shows me all the things that are called drop or have drop in the name, and it shows me all the types of those things. So it's a structured object that you can query and you can update and edit to your heart's content. so this code-based model and the sort of code-based editing is like a whole other talk, and I'm not going to be talking much about that. But I just want to quickly give you the flavor of this sort of structured code-based approach. So it gives us incremental compilation that is perfectly precise, and it comes pretty much for free. Like, you'll never spend time waiting for your code base to compile. Like, once something is compiled, it remains compiled forever. Like, you've found the hash, you can just have the hash and the compiled code in your code base, and no one will ever have to compile it again. Right, so no matter how large your code base is, you'll never be like, recompiling it. Refactoring is also kind of a different experience. It's more of a controlled experience. And you can make it so that refactoring always type checks. Like, you do a little refactoring and everything type checks, and then you do a little more until you've done the sort of the full work of your refactoring. And the Unison sort of codebase tool will help you understand how much work you have remaining until you've completed your refactoring. Arbitrary changes to the codebase can be completed without dealing with like a depressingly long list of type errors, for instance. Like, you change one definition and now like you have 72 type errors on your screen. That's not going to happen. So codebase changes can be worked on concurrently by multiple developers. So many situations that traditionally result in merge conflicts or build issues are not going to occur. We're not going to have builds, so that's not going to happen. And then renaming is trivial. Like, even bulk renaming is 100% accurate and completely fast. And there's kind of a cool thing there, which is that when it's this easy to rename things, there's a lot less anxiety about like naming and picking the right name for something. You can always just change the name later. And if you change the name, that's not going to break anybody else's code. They can still use the code because their code refers to the hash. Okay. And so also, dependency hell is vastly reduced. So many situations that contribute to dependency hell just simply don't arise in the Unison codebase model. So let me show you that here real quick, the dependency hell situation. So most dependency hell situations come up because of this sort of diamond dependency problem, right? So your program depends on some library A and some library B, and both A and B depend on some library C. Great, but now they diverge, and now they depend on two different versions. So A depends on version 3 of library C, and B depends on library C version 4. And so now you get a build error, so you end up with a conflict, and your program no longer works, at least in many systems. So much of the time, this problem is just that libraries aren't granular enough. All right, so the situation where library A and B actually depend on totally different parts of library C. So here on this slide, like, A is talking about c.foo, and B is talking about c.bar. So it doesn't matter if they're different versions, because they're not going to overlap in any way. So that should just work anyway, and in Unison it does. Because Unison actually tracks dependencies at the level of individual hashes. So there's no sort of like big module library full of things. You can track the dependencies on the individual hashes. So the dependency actually kind of looks like this. Like, your program depends on some hash and some other hash, and those hashes depend on some other hashes, and like everything just works as long as you're not trying to do anything crazy. So like, even if your program talks about library A and library B, and they're both talking about c.foo, but they're talking about two different versions of c.foo, that's totally fine as well, because c.foo version 3 and c.foo version 4 are actually two different types, and they have two different hashes. And so as long as you never try to pass off version 3 as version 4, you'll be fine. But if you try to do that, then Unison will give you an ordinary type error. Great. So speaking of type errors and types, I'm going to tell you a little bit about Unison's type system. Okay, so Unison's type system is this. Complete and easy bidirectional type checking for higher rank polymorphism, which is a paper by Josh Dunfield and Neil Krishnaswamy. So we've implemented this paper as our type system. It's very similar to Haskell. It supports type inference, higher rank types. It's great. I'm not going to go into the details, but it's just awesome. We also have harvested the idea of type error provenance from a talk by Leonard Augustin. And this lets us tell the programmer where a type error originally came from, which is kind of cool. And I'm going to show you that here in a bit. So this actually lets us give really good error messages, at least in theory. So I promise that when you're working with Unison, you will not have to look at pages and pages of type errors. But when we do give type errors, we want them to be good. We want them to be helpful. Because like, it's kind of funny that we're nearly like a quarter way into the 21st century, and still compilers are just like giving errors like it's the 1970s, and we only have 16 bytes of memory, and they're just like error code 74, whatever. But like, you know, we can do a lot better. So I think error messages generally are needlessly technical and terse, and sort of inspired by Elm, we are, you know, trying to give really good errors that will help you repair your program. Okay, so ideally, I think that an error should read like another developer explaining the problem to you. Like that's probably a lot to ask, but I think that that's sort of like the ideal we should strive for. So here's a programming language not doing that. So I'm picking on Haskell because Haskell is my favorite programming language, you know, after Unison, and it's the language that I use most. So most of Unison is implemented in Haskell. Okay, so here's Haskell giving you a cryptic type error. So I've actually, you know, I used two different types, for and an int and a string here in this case expression. And Haskell is like, okay, well, there's no instance for num list of car arising from the literal for. And then it tells me all kinds of other stuff. And I'm like, what does that even mean? Okay, so, and then Unison is just like, okay, all cases of a case-of expression must have the same type. And so this reads a lot more nicely. And it tells you like, well, one of them is this and the other one is that. So please fix. I just want to do a little dig at Scala because, like, you know, I love Scala. So here's what Scala does. So, you know, you do case 3 is 4, case 4 is surprise. And Scala is like, okay, cool. Scala is way ahead of the game. Like, this isn't even a type error in Scala. All right. Okay, so I think that an error should help you repair your program. It should take you towards the, you know, a solution to the error. So here's Unison doing that. So here I'm saying, I wanted to say hello followed by, you know, the name that I got. So I say write hello, and I wanted to say hello plus name, but I forgot to put the plus. And Unison is like, well, this looks like a function call, but there's a text where the function should be, are you missing an operator? And I'm like, yeah. Yeah, actually I am. And Haskell is like, well, couldn't match expected type car with whatever. And then it's like, relevant bindings include, and it gives me a lot of irrelevant bindings, like below here. But like, I mean, it's like lots of them. Anyway, here's another one. Like, I forgot to put parens around the plus here. And so it's like, non-type variable argument in the constraint, something really complicated. Use flexible context to permit this. I'm checking the infer type. I have no idea what this means. So like, where do I even begin? And Unison is like, not really sure either, but it's like, I'm not sure what plus means here at line 1, you know, and it's highlighted here in red. So whatever it is, it has this type. And it's like, I found some terms in scope that match that name, but they have different types. If one of these is what you meant, like, put that in, and like I might be able to give you a better error. And in the future, I think we might, you know, we'll have better facilities to do this automatically. But for now, it'll be just like, try these things and see what you get. And so I'm like, okay, I'll try nat.plus. And then it's like, okay, nat.plus needs a nat, but you've given it a list. So it's still not telling you like, oh, you forgot the parens around the plus, but it's, you know, it gives you a better hint at what's happening. So I think, you know, we can improve this error, but it's pretty good. So in general, I think we want to tell the user where the mismatch was, which types were involved, and then where those types came from. Why did Unison think that, you know, those types were involved in the first place? So for example, here, I'm applying a function foo to some arguments, and they all have to be of the same type, but I've used 1, 2, 3, and then hello and 5. And so Unison tells me, well, okay, the function has this type. It takes a bunch of arguments and returns a value of that same type. And it says, like, I think A is nat, and I think it's that because I found a nat here. So nat is the type of natural numbers. So like, I think you want natural numbers here, but like there's a string for some reason, right? So that, and it tells you why it thinks that. So I think that's super helpful. So also, if the solution to an error is trivial or obvious, Unison will just fix it. It will not tell you about it and nag you to fix it. For instance, if a name is ambiguous and only one of the names that creates that ambiguity type checks, Unison will just pick the hash that type checks and not bother you anymore. All right? It will just assume you meant that hash and it will just use it. But if a name is ambiguous and more than one solution type checks, it will nag you and it will tell you all the things that it knows that fit in that type. So this incidentally gives us type tolls for free. So like if you are not sure what you can put in a particular place in your program, you can just put some nonsense and it'll tell you the type of the thing that should be there. Like for instance here, I misspelled append, and it's like I'm not sure what append means here, but whatever it is, it has this type. So I could have put anything in there like foo, and it will say like, okay, well foo needs to be this type in order to fit here in this program. Cool. But I'll very quickly tell you about another thing that we wanted to be thoughtful about, which is Unison's effect system. Because let's be honest, monads are awkward. All right, I said it. So monads come with syntactic overhead, and they also come with a cognitive overhead for the programmer. And so what we've done is, in Unison, we've implemented algebraic effects, sometimes called that. And we modeled our effect system on a language called Frank, which is detailed in this paper, Doobie-Doobie-Doo, by Sam Lindley, Colin McBride, and Craig McLaughlin. Frank calls these abilities, and so we do that as well. For example, here is state ability. So this is the ability to put and get some global state of type S. So abilities are introduced with this ability keyword. And so this is the state S ability, and it has two things that you can do. You can put the state of type S, or you can get the state of type S. So put takes an S and gives you a unit, given that you have the state S ability, and get will give you the S, given that you have the state S ability. And so then you can write effectful functions that push and pop, for instance, given like a global stack. So there's no monadic plumbing here, you'll note. This is just like blocks, and so this looks like an imperative program. So pop is just like get the stack, and then put the tail of the stack, and then get the head of the stack and return that. And push is put the thing on the front of the stack. Great. So we can do this in Unison because applicative programming is sort of the default, right? We kind of overload the function application syntax for both effectful and pure functions. So it's not that we're having side effects. It's just that the function application syntax, which is just space, by the way, it works for both pure and effectful functions. So for instance, in Scala, if you wanted to work with an effectful function, say you wanted to work with some effectful things x, y, and z, and you wanted to apply some function f to those, you would have to do this, like a comes from x, b comes from y, c comes from z, and then yield f, a, b, c. But in Unison, you can just apply f directly to x, y, and z, right? Same in Haskell, you might have to use this sort of applicative syntax, but in Unison, the applicative syntax is the same as the function application syntax. So you just directly apply the function to your arguments. And it doesn't matter where in your sort of effect stack you want things to be. Whereas in Haskell, like you have to know like the order of where things are, and so like, oh, I gotta lift and hoist and stuff. But in Unison, you just say, well, it's just function application. And then, instead of monadic bind or like Kleisli composition in Unison, that's just regular function composition. Cool. Yeah, we can write like programs that do cool stuff. We can write like a little program that pushes and pops the stack using our state ability. So here, this program, A is the head of the stack. We pop the stack, and now we've sort of mutated the stack, right? And then say, okay, if A is 5, then push it back. Otherwise, push 3 and 8, all right? So this looks like a little imperative program, but it's actually a purely functional program. There are no side effects here, but there are also no visible effect plumbing here, right? So it's kind of nice. Then we have to tell Unison what does this state ability mean? So we have to provide that ability at some point. And this is something that will be provided by library authors. Generally, if you're just writing applications, you'll probably not be writing your own handlers like this. But if you do want to, you can. So here to handle the state ability, in the middle of the slide, you see I'm saying here in my state function here, I'm saying handle with h of s in, and I'm saying bang C, which forces the computation C. And C is a quoted computation. You can see that it has that little tick on the type. All right. So what this is doing is that the expression at the bottom here, the handle h of s in C, is what's happening, and then the definition of h is just above, and that actually proceeds to pattern match on the constructors of the ability. So it's like, okay, if the programmers said get, then I get a k, which is the continuation of the program. That's the rest of the program. And so what's expected is that I pass the current state to k. That is, I allow the program to continue with the new state. I mean, with the current state. So I say, okay, well, if there's a get, then I call k of s, and this is a recursive definition. I keep trying to handle if there's any more state manipulation going on. And then if it's a put, then I get some s, and I also get a k, and now I want to pass the new s to my handle h, and I call the continuation of the program with unit. Okay, so it's non-trivial, but it's pretty nice, and it allows you to sort of customize these sort of abilities. And then at the end of the day, let's say I have some stack program that I've written, and then I want to run that given some initial stack, which is here 5, 4, 3, 2, 1, and I just say state of that initial state and my stack program, and that runs that stack program given that initial state. So it sort of simulates global mutable state. But I can also use like actual global mutable state. I can like use I/O to do things. So here, example, I'm implementing a receive ability in terms of an I/O ability. So here, I might receive a program. I might get a program at R as an argument that requires this receive text ability. That is, it might send me requests, which is like receive.receive, which is a request from that program for some text. So I need to pass some text to K, and here I am just passing readline, which is an I/O effect. All right, so I'm basically translating this receive text program to an I/O program. So you can handle abilities into other abilities. So that's pretty cool. Great. Anyway, this is super flexible and kind of awesome. So yeah, if you try to use, for example, I/O in pure code where you don't have that ability, like for instance at the top level, I try to say I/O.readline. Unison will give me an ability check failure. If you like D&D, then you'll appreciate that. So it does an ability check, and like there are no global abilities. You have to handle stuff in order to introduce abilities. And so if you try to do I/O at the top level, you will get a type error like this. Cool. But you can still use Monads. So Monads are still available. Monads are still cool. I'm sorry, Monads. I didn't mean it. But yeah, so you can still use them, and they'll be great. So then again, why are we making a new language? Like instead of adding to, for instance, Haskell or an extinct language. And I think it's this stuff about names that we can't really implement. But more than that, I think Unison is not so much about features that we want to add to the developer experience. It's really about what we want to remove. We want to take away from the developer experience and strip away the non-essential, the frustrating, all the friction, and just sort of distill programming to the joyful essence that it was always meant to be. All right. Right, so status, where are we with this? So as of right now, November 2018, you know, we have implemented a lot of stuff. We have bidirectional type checking, we have type-directed NIM resolution, we have like algebraic data types, patterns, we have this ability system. It's polymorphic, so we have ability polymorphism. We have, you know, pretty good type errors, and we have type errors that are structured objects. So we don't really just have error messages, so it's not just like a string. When we throw an error, it's actually like a full trace of like what the type checker has done, and so we can generate a good error message from that. We have type error provenance. That is, we can detect where a type originally was introduced that caused an error. We have a native runtime that we wrote in Haskell, and we have a JVM-based runtime that we wrote in Scala. So that's great. You can run either natively or JVM-based. We have this cool thing that, you know, I might have time to show you, which is, we're calling it an edit eval print loop. So instead of a REPL, you just use like a text editor to edit stuff, and then you save the file, and Unison will pick up the stuff that you saved. It's pretty cool. And then we have this command line code-based manipulation tool. And yeah, don't call it a build tool, because like we don't build anything. But it's the thing that allows you to manipulate your code base, query it, and branch and merge and things like that. Okay, so in the near term, we're hoping to implement the actual distributor runtime. That's not done. We need to add core libraries. There are basically no libraries yet. Like, we need to add libraries for lists. Well, we have a bunch of things for lists, but we also have a bunch of things for streaming, but we need to add more. We need things for storage and I/O. We need distributed data structures. And like, somebody needs to write those. And so like, if you want to contribute, then you could potentially have a huge impact on this ecosystem. We need documentation. We need a formal specification, because we're still sort of making things fit. We need glitter and sparkle, obviously. And I don't even have any glitter in my hands. Okay, so we need sweep-looking websites, obviously, with tutorials and examples. You know, all the things that a good language needs. We're hoping to have a release of Unison, like an alpha release that people can usefully use. So our current target is to make a language that makes us not want to throw out our computers. And then we want to, you know, in spring of 2019, have a language that makes you not want to throw out your computer. All right. So it might be good enough for us to use for now, but we want to make it good enough for you. All right, so in the meantime, if you want to know more and if you want to follow our progress or maybe help out, if you want to contribute to the development of the Unison language, please come talk to me during the conference. We're really early in this, so, you know, again, your contribution could make a huge impact. So check us out at unisonweb.org. Thank you.